Hi, this is Remembering the Past, the show where we talk about people who've died recently who've had a profound effect on our history, our society, or our culture. And in our ongoing series of Nobel Prize winners, tonight we're going to talk about one of the great scientists of the 20th century. A couple of weeks back, we did one of the great biologists of the 20th century, Sidney Brenner. Tonight, we're going to talk about one of the great theoretical physicists of the 20th century, Murray Gell-Mann. Murray Gell-Mann died recently at the age of 89, and he was awarded the 1969 Nobel Prize in Physics for his contributions and discoveries concerning the classification of elementary particles and their interactions. I still don't know very much about theoretical particle physics, but you do enough of these and you get to learn something. According to Nobelprize.org, during the 1950s and 60s, new accelerators and apparatuses helped identify many new elementary particles. In theoretical works from the same period, Murray Gell-Mann classified particles and their interactions. He proposed that observed particles are in fact composite, that is, comprised of several smaller building blocks called quarks. According to this theory, as yet undiscovered particles should exist. When these were later found in experiments, the theory was accepted. Dr. Gell-Mann realized that the classical description of the atom is made up of a proton, a neutron, and a nucleus was overly simplistic, and so when he proposed these even smaller subatomic particles, Dr. Gell-Mann decided to call these subatomic particles quarks, after a line from James Joyce's Finnegan's Wake, 3 quarks for muster mark. Here's a recording that should go down in the annals of science with Murray Gell-Mann talking about the origin of the word quark.
Well, let's see. In the citation for the award, it was barely mentioned, but I did propose that the neutron and proton and the related baryon were composed, roughly speaking, of 3 quarks each, and that the quarks were the fundamental entities there, analogous to the electron. The neutron, proton, and so on were not elementary. The word I had first as a sound, quark. It might have been spelled Kwork. But then I thought it was the right sound for the fundamental constituents of nuclei. Sounds good, quark. Then I discovered the word quark in Finnegan's Wake, and with the number 3 also. There are, roughly speaking, 3 quarks to a nucleon or a baryon. I thought, well, perhaps I could use the spelling there, Quark.
We'll talk about how brilliant a guy Murray Gell-Mann was in a second. One of the legends was that he gave his Nobel speech in Swedish, but here he gives you the truth. And it wasn't Norwegian either.
One thing about winning this award is that it increases the number of stories that people make up about you. No, what happened was that when I talked at the banquet after the award ceremony, one paragraph was in Swedish.
Now, I have to tell you that Murray Gell-Mann was one of the great prodigies that we've discussed. He was a nice Jewish boy born in New York City, and he graduated high school, Columbia Grammar, at 14 as valedictorian and went on to Yale. He was born too late to be part of the Manhattan Project, but I can pretty much guarantee if he was born a decade earlier, he would have been right in the middle of it. In any event, he worked with or hobnobbed with all the big names in post-World War II physics. Let's see, after he graduated from Yale, he got his doctorate at MIT. Then J. Robert Oppenheimer recruited him for Princeton and the Institute for Advanced Study there. I'm guessing he met Einstein while he was there. Then he went on to the University of Chicago where he worked with Enrico Fermi. Later on he went to Caltech where he worked with Richard Feynman before he struck out on his own. So nobody has a better post-war pedigree than Murray Gell-Mann. And believe me, he held his own with all of these guys. He believed there was an underlying harmony and an underlying beauty to subatomic particles, but it needed new concepts and new mathematics to read it. The new mathematics which he introduced was more unfamiliar than the matrix algebra which had founded quantum mechanics and was more difficult for physicists to domesticate and master. The new mathematical tool that Gell-Mann introduced to physics was called group theory. As it happened with quantum mechanics and matrix theory, it had been around for a century. It had been formulated by a young French mathematician, Évariste Galois, who wrote out his ideas the night before he was due to take part in a duel. Galois was killed, but his ideas lived on, eventually to form the basis of our current understanding of the particles from which the universe is built up. Gell-Mann noticed certain patterns amongst the newly discovered particles when their properties were displayed on a graph. They seemed to fall into certain families or groups. Galois' group theory applied exactly to this kind of mathematical setup. Although other physicists were skeptical about Gell-Mann's patterns, he pointed out that the theory indicated a whole, a place in the pattern which should be occupied by a particle with certain properties. In 1964, experimenters at Brookhaven National Laboratory discovered this particle, and Gell-Mann was proven right. Fundamental particles do form families, but group theory was a stronger tool than this. It laid down rules governing the relationships in the family groups, how you would need to alter one particle to turn it into another of the same family or pattern. Gell-Mann found that this mathematical device, which evidently worked so well, corresponded to a simple physical interpretation. The fundamental particles produced in the particle accelerators are composite. They are made up of smaller entities, and those are what we know as quarks, which were confirmed directly in an experiment at the Stanford Linear Accelerator Center in California, the SLAC. He got deeper into quarks and into superstring theory, but he was a quirky guy as well as a quarky guy. He didn't always get along with everybody. He didn't get along that well with Fine. Boy, I'd love to have seen some of those fights. And after he'd won every award there was to win, he sort of left the field to cultivate different interests. One of them was linguistics.
I'm very interested in languages, and I know something about the relations among languages, about etymologies, about sound changes from one language to another, and so on and so forth. I'm very interested in that, and even helping a little bit to work on it. But as to speaking languages, any European waiter could do much better than I.
He also developed an interest in biodiversity.
In trying to preserve the heritage of biological diversity. I'm also somewhat interested in the preservation of cultural diversity, although that involves a great many more paradoxes and contradictions. I've worked hard on trying to help with the preservation of biological diversity around the world. And of course, on land, the greatest diversity is found in the tropics. And also the tropics are full of poor and, in many cases, overpopulated countries. What is most important to preserve is in the tropics, at least on land. And also the dangers are greatest in the tropics. So a lot of our work has concentrated on the tropics. I've worked mostly through the John D. and Catherine T. MacArthur Foundation, based in Chicago. It was a very great field ornithologist, Ted Parker, who joined me over a campfire in Venezuela when we invented the idea of the rapid assessment program, which has been quite useful in nature conservation. The idea is if a certain tract of land is considered for possible preservation as a national park or whatever, how to evaluate the diversity that's present and the quality of the environment. To what extent is this a natural area worth preserving? Now, the old-fashioned way, of course, of looking at an area was to have skilled botanists and skilled zoologists of various kinds spend many years cataloging the various species and their interactions with one another and so on and so forth. The trouble is, by the time you do that, the area may not exist anymore. So what we did was to champion the notion of having certain very special field biologists, like Ted himself, form teams to go in and rather quickly and approximately to evaluate the diversity and the quality represented by the area.
Not too many theoretical physicists discussing biodiversity. Later in life, he strayed away from classical theoretical physics into a field he called plectics, about simplicity and complexity, and he wrote a classic book called The Quark and the Jaguar. Here he discusses the nature of simplicity and complexity and the fundamental organization of the universe.
Simplicity and complexity, regularities and randomness. This subject, which I call plectics, the study of the simple and the complex, includes a good deal that has to do with physics. Plectics comes from the common root of the word simple and the word simplicity and the word complexity, without specifying whether you're talking about the simple or the complex. I used to work on the simple only, that is, the fundamental laws of nature, which we believe are fundamentally simple. Yeah. But we see around us a great deal of individuality. We see around us adaptive evolution, as in biological evolution, for example, but also cultural evolution, evolution of ideas, and a great deal of individuality. These are not things that one finds directly in the fundamental laws of physics, where, for example, every electron is exactly identical with every other electron in the universe, and where we believe, at least, that the laws don't change with time. The fundamental laws are immutable. In fact, some people now claim, just in the last few months, that they have found some evidence that some of the supposed constants of nature are actually changing very slowly. But if true, that would be a very slow cosmological effect. But in the world around us, we see lots of individuality and a great many different kinds of evolution and so on and so forth. And we see a lot of complexity. So where does that come from? And in my book, Kvarkin och Jaguarin, The Quark and the Jaguar, I discuss this question. But the point is that the fundamental laws are simple, but they are not deterministic. Even at the fundamental level, they're not deterministic because of quantum mechanics. But besides that, they fail to be deterministic because no observer anywhere in the universe can have access to all the necessary information for predicting the future. In other words, any observer sees only a coarse-grained version of the universe, and the coarse-grained state at a given time does not determine the coarse-grained state at the next time, only probabilistically. So we have to look at all the alternative possible histories of the universe as a branching tree of possibilities with probabilities at the branching. The great writer, the Argentine writer Jorge Luis Borges, wrote a story about somebody who made a model of the branching alternative possible histories of the universe in the form of a garden of forking paths, el jardín de senderos que se bifurcan. This idea that the alternative possible histories of the universe, coarse-grained, of course, form a branching tree means that the history that is actually seen is co-determined by the simple fundamental laws and by an inconceivably long sequence of accidents or chance events, which can come out in various ways. In advance, one can predict only the probabilities of the different outcomes. So there, of course, is the source of complexity. Now, some of these accidents produce a great deal of regularity in the future. And those we can call frozen accidents, things that, at least locally in space and time, create new regularities in addition to the fundamental laws. Now, fundamental physics relates to the basic laws, but the rest of physics and chemistry, and especially other sciences like biology and geology and so on, and observational astronomy and so on, all of these depend a great deal on the accidents, not just on the fundamental laws, but on all the rest of the information that contributes to the history of the universe. The fundamental laws give you the probability, but you have to adjoin to that information a lot of information about the accidents that have already occurred, and especially these important ones, which we can call frozen accidents, which create a great deal of regularity in the future. And by complexity, then, what I call effective complexity, we mean the length of a very concise description of the regularities of something.
Well, I'm going to close on that note. I want to thank my producer and IT genius, Sid Tepps. Later in life, when Murray Gell-Mann retired from Caltech, he moved out to New Mexico, and one of the things he did was take up bird watching.
Oh, there are many species. I've seen less than 4,000 out of 9,600 or something like that, almost 10,000 species that are recognized in the world. But there are a few special ones that it would be wonderful to see. The Congo peacock, for example. For a long time, nobody could believe that there was a peacock in Africa. No European had actually seen one alive until quite recently. Saw them in the Regent Park Zoo. It's probably the only place in the world where you could see a Congo peacock in captivity. But it would be wonderful to see one in the wild.
So as a final tribute to Murray Gell-Mann, we're not going to watch birds, but we're going to listen to one Charlie Parker. And as they used to say, if Charlie Parker were a gunslinger, there'd be a lot of dead copycats. Here's Charlie Parker with a little Gershwin. And as you could say about Murray Gell-Mann's Nobel, they can't take that away from me.